penuh bervisi guru AYU mencapai misi yang satu, permisi kita bantu.
Tahniah, siaran langsung ini dibawakan khas kepada anda oleh Akademi Youtuber Malaysia. Tumpukan perhatian anda, siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Hi, salam sejahtera dan good evening everyone. Welcome to Pusat Tuisyen Akademi Youtuber with the joint venture of e-Didik Malaysia and Crowd Guru Malaysia. Bermula percuma, selamanya percuma. I am Mr. Peh. Currently, I am teaching at College Tingkatan 6 to Fatimah Melaka. I am the teacher on duty for this week. For your information, we have 2 classes of physics conducted in this week. On this Friday, we have the class Form 4, which is presented by teacher Slinda. If you miss out the class, you may visit the channel of teacher Slinda for the lesson. And another lesson will be on today, and the class will be conducted in DLP for Form 5 class. And for today's lesson, this is expected to complete within 1 hour. And the e-sigil link will be provided at the end of lesson. Please fill up the link e-sigil within 30 minutes. And the link will be provided at the end of the lesson. So without further ado, so today we are going to our last chapter, which is a chapter 7, quantum physics, with the subtopic of 7.1, quantum theory of light. And in today's lesson, we are going to learn about 5 learning standards. Okay, so the first learning standard, you have to explain initiation of the quantum theory. Okay, so before we go for the idea for spark of the quantum theory, let us look at the electromagnetic spectrum, where actually you have already learned in your Form 4 syllabus, Chapter 5, subtopic of 5.7. Okay, so you can just look at this figure. So this will be the electromagnetic spectrum, and it is a continuous spectrum. So where there will be no any gap between different type of spectrum. In this spectrum, it consists of 7 types of wave. So first will be radio wave. Second will be microwave, infrared radiation, visible light, ultraviolet ray, X-ray, and gamma ray. So the arrangement of each spectrum will be arranged in increasing wavelength, or you can see another parameter will be using frequency. So the radio wave will has the lowest frequency and longest wavelength. Okay, so here, the hot object is emitting the wave with higher frequency, such as visible light and ultraviolet radiation, while the colder object, they will be emitting the wave with lower frequency, which will be radio wave or microwave. So the frequency of the energy is directly proportional to the temperature. Thus, if we compare the color of light in visible region, so the red color of light which have the longest wavelength or lowest frequency has lower temperature. On the other hand, the white blue light will be has higher temperature as it has the shorter wavelength and highest frequency. Okay, so here we go to definition of the black body. Okay, so what is the black body? Okay, so a black body is an idealized body or surface that able to absorb all electromagnetic radiation that fall on it. So just now we already explained. So there are 7 spectrum in the electromagnetic radiation, which is, for example, we have the infrared, we have visible light, we have gamma ray and others. Okay, so the black body will be absorbing all the type of the electromagnetic wave where is fall on it. So you can just look at this figure. Okay, then the idea in the definition means that what is absorbed, the same type of the radiation will be also emitted. So you can see here when there is a light strike to the surface of black body, so there will be no any reflection of the light. However, there will be have the thermal radiation will be emitted when the body have higher temperature. Okay, so a black body, as mentioned, can also emit thermal radiation where it's depending on the temperature. Okay, so in the line here we have Jimmy. Okay, so hi Jimmy, welcome to my lesson. Okay, so you can look at this figure. So the different black body, okay, we can mention that as black body. So when they have the different surface temperature, so they will be emitting different type of thermal radiation. As we explained just now, the hotter object will be emitting the radiation with a shorter wavelength, while the colder object, it will be emitting the radiation with the longer wavelength or lower frequency. Okay, so from here, the radiation emitted form a continuous spectrum and is unaffected by the nature of the black body surface. Okay, if you look at this black body curve, okay, this one we know as a black body curve, where the y-axis is radiation intensity, then the x-axis will be the wavelength. Okay, so in comparison with these 3 different styles, the blue style have the highest temperature, body temperature, which is about 8,000 K. Okay, while the lowest will be the red star, so with the surface temperature of 3,000 Kelvin. So the intensity maximum emitted by the blue star is brighter, and you can see the maximum intensity is dropped at the wavelength, which is shorter compared to the red star, which has the lower temperature. Or you can see if I extend the maximum point, so here is the maximum intensity emitted by the blue star. You can see the wavelength is actually shorter compared to the red star, where it has the longer wavelength. Okay, so in conclusion here, the brighter or the higher intensity emitted by the black body, it will given or emitting the light which is have lower wavelength. Okay, so here will be the summary. As the temperature of object rises, the object act as black body radiation. So they will be emitting the thermal radiation. Okay, so here will be with all wavelength. So according to this diagram, which is the radiation intensity against the wavelength. So there are three types of black body for this comparison at different temperature. Okay, so when the temperature increases, the wavelength approaching maximum radiation intensity will get shorter. So just now, actually, I already explained. Okay, so you can look at this point. So this is considered the maximum intensity, okay, emitted by the blue star. So where it has the highest temperature. So the wavelength will be approaching with the shorter wavelength if you compare with the red star, which has a lower temperature. Okay, so a star with temperature of 8,000 Kelvin is brighter. Or will be this. And look bluer with the light have the shorter wavelength compared to the star with the temperature of 3,000 Kelvin is dimmer, or we can mention that the intensity of radiation is lower, and the color appear here will be redder where the radiation with the shorter wavelength. Okay, so thank you also for Cikgu Hasnitah for joining my lesson. Okay, so then the next will be number 8. Okay, so the black body curve is actually can use as thermometer to determine the temperature of the distant object. So here you can just look at this figure. Okay, so here the first will be the interstellar gas cloud. So it has the lower temperature compared to very young star will be the second, higher temperature with 600 Kelvin. Then the next will be sun surface, and the brightest star will be given the highest surface temperature. Okay, so for example here, the relative cold surface, if we compare by using the very young star, so where it's measured with 600 K, so it emits mostly infrared, and the wavelength will be actually longer, or you can mention that the frequency is lower. Okay, so if we compare to the brighter star, so which will be this? So you can see the surface temperature will be about 60,000 Kelvin. Okay, so the ultraviolet radiation will be emitted. Or you can see at the highest peak. Okay, so here the wavelength for the light emitted or radiation emitted will be have shorter wavelength. Okay, then example of the black body in daily life. So besides just how we explained that the black body curve can use as a thermometer to determine the temperature of the object at distant position. Okay, so actually we have a lot of black body example in our daily life. Okay, so the first here will be the oven heating elements. Okay, so you can see these parts, the heating element is in brighter color because of emitting the radiation with certain wavelength. Okay, then here the second example will be the thermal scanner camera infrared. Okay, so the last comparison here will be the thermal radiation in the light bulb at different temperature. Okay, so you can compare the intensity of the light for these two bulbs. So the left side of the bulb given dimmer of the light emitted. Okay, because the temperature of the bulb is lower, so it emitting the light which is a longer wavelength or lower frequency. So on the other hand, for the right side of the bulb, So you can see the intensity of light emitted is higher. This is due to the surface of the bulb for the right side bulb is actually higher. So it will be emitting the radiation with the higher frequency or lower wavelength. Higher frequency or lower wavelength. So which will be given brighter light. Okay, so the light emitted is due to its temperature or body temperature. Okay, so we can conclude that these three type of example is actually the black body. Okay, because they are absorbing all the radiation without reflect the radiation, but they're emitting the thermal radiation when their body or their surface with the higher temperature. Okay, so here I given few example of non-example of black body in daily life. Okay, so the first you can see here, this is the moonlight. So moonlight is not considered as a black body. Okay, because the light emitted is due to the reflection. Is due to reflection of the light. It's not because of the moon surface have higher temperature. Okay, so besides that, we have another example of the light produced by insect. Okay, so this is also non-example of black body. Okay, so the light emitted is due to the bioluminescence screen. Okay, so in conclusion, the non-black body will absorb the light and reflects back the light and not emitting the thermal radiation. Okay, because they don't have a higher temperature in their body. Okay, so here, after you understand about the black body, so where we also discuss about the black body curve. So this is a graph where we draw or we compare the intensity of light against the wavelength or frequency or sound of the light. Okay, so we this. Okay, so here we want to compare what is the contradict between the classical theory and the quantum theory we want to discuss today. Okay, so according to classical theory, the electron vibrating at the same frequency should have the same energy content. Okay, so the vibration frequency of electron also has no limits. Okay, so you can look at this curve, which is according to the classical theory. Okay, so you can see classical theory predict that the frequency increases is actually bring the same meanings where the wavelength is actually getting shorter. So the radiation intensity of the black body increases indefinitely at any temperature. So you can see the curve expected will be this, where when the wavelength decreases, so the intensity of the radiation will be keep increasing. So this is what expected by the classical theory. Okay, so however, the experimental result involving black body radiation are inconsistent with the classical physics theory. So where will be the graph? Just now I showed you already. So this is the actual graph for the black body curve. Okay, so based on the graph, the intensity of the light on the left side, so where I already boxed with red, is actually not continue to increase with the frequency of the wave. Okay, so you can see here, this side with the shorter wavelength will be showing or represent higher frequency. So when the frequency is higher, if we compare with the curve, which is with red dashed line, so it will be given increasing of the intensity when the frequency increases or the wavelength decreases. But through the experimental result, we showing the curve and the left side here will be showing decreases of the radiation intensity, although the wavelength is decreases or frequency is increases. So this is actually showing different result if you using the classical theory. So therefore, the theory of classical is failure to discuss about the result we get on the black body surface. And this introduced to a new theory where we are going to discuss today will be the quantum physics theory. Okay, so before we go for the detail about the quantum theory, let us discuss about the scientists involving in the classical theory. Okay, so the first will be the Isaac Newton. So he described the particles nature of the light. However, he unable to explain the refraction of the light. Then the second, the Thomas Young, he shows the light as a wave through the light diversely experiment. So this experiment actually you also already learned in chapter form 5, chapter form 4, 4.3. Okay, so will be this experiment where showing the diffraction and the interference effect. Okay, so however, he also unable to explain the black body radiation spectrum. So where just now we explained already. So the black body radiation will be in curved shape and given lower intensity when the frequency of light increases. So the next will be the John Dalton. Okay, so he gives a theory about the atom as a smallest particles of matter. Okay, so but he unable to explain the light spectrum produced by the atom, which will be the continuous spectrum. Then the next will be the J.J. Thomson. So he is the person discover the negative charged subatomic and known as electron. He also unable to explain the line spectrum of light produced by atom. So will be this discrete spectrum. Okay, so here we discuss the scientists where is involved in the development of the quantum theory. Okay, so the first will be the Max Planck. So he introduced the idea of quantum as a packet of discrete energy. So you can look at this figure. Okay, so the light will be in the packet with energy. And we are going to discuss detail at Learning Center 2. Okay, then the next will be the electromagnetic wave emitted by black body is in discrete packet, which is known as the quantum energy. Okay, and he also introduced the formula where relate the photon energy to the frequency. Okay, then the next will be the Albert Einstein. So he developed the Planck's theory by stating that light exists in quanta, which is known as the photons. Then from the equation developed by Max Planck, Einstein relate the kinetic energy of the photon electron they are emitted with the light frequency. So he also discovered the photoelectric effect, and this will be going to discuss in subtopic of 7.2. Okay, the next person will be Niels Bohr. Okay, so he is the person who able to explain the line spectrum produced by the hydrogen. And this is actually unable to explain by J.J. Thomson, just how we explained already, who is the one involved in development of classical theory. Okay, so the photons are emitted when electrons transfer from one higher energy level to lower energy level. So you can look at this figure. Okay, so this theory is developed by the New Bohr. Then the next will be the Louis de Broglie. So he introduced the hypothesis that particles can also show wave particles. This will be going to discussion in detail in Learning Standard 4 and 5. Okay, so the Einstein and de Broglie postulated the idea of wave particles, duality of light, and all subatomic particles. Okay, so this is 4 persons who contribute to the development of the quantum theory. Okay, so here let us discuss the first question, which is related to our Learning Standard 1 today. So students, you may show your answer in the chat room so we can compare your answer together with me here. Okay, so which of the following pair correctly show an example of radiation emitted by an object? Okay, so just now we have already discussed the lower temperature object will be emitting the light with higher, lower frequency and longer wavelength. Okay, while for the object with high temperature, so the radiation emitted will be with higher frequency but lower wavelength. Okay, so which answer suppose you have to select in this option? Okay, so here we have to compare. For A option, the microwave and the radio wave. So the radio wave is actually longer compared to microwave. Okay, so the option A will be wrong already. Then for the second, the UV ray will have a higher frequency, shorter wavelength. So it will be also not meets the requirement for low temperature object, which is actually need to emitting higher wavelength of light. Okay, so the B also wrong already. Okay, then the C here, the radio wave will be actually longer wavelength, while visible light will be given us the shorter wavelength if we compare with the radio wave. Okay, so the answer expected will be actually C, right? Okay, then the ultraviolet ray for option D, so is actually shorter compared to visible light. So the answer is very clear, it will be C. Okay, so this will be the temperature, just now explained already, increases, the object will be emitting the radiation with a higher frequency or shorter wavelength. So answer here will be C. Okay, then the next question here will be question related to trial 2022 for state of Terengganu. Okay, so this is actually the section A question number 4. Okay, so diagram 4.1 shows a black body radiation curve. Just how we already discussed about the curve. Okay, so mark with tick for the correct answer in the box provided. Okay, so the black body are the idea of the electromagnetic radiation. So it is absorber, radiator, or absorber and radiator. Okay, so actually the definition just now we have already explained. Okay, so this will be a black body is a idealized body that is able to absorb all electromagnetic radiation fall on it, and it also will be emitting thermal radiation, which is depending on the temperature. Okay, so therefore the key word here will be this. So black body will be absorb all electromagnetic radiation. So it is an absorber. So on the same time, it will be also emitting the thermal radiation, which will be depending on its temperature. So this will be radiator. Okay, so answer should be absorber and radiator. Okay, then the next question B. So will be like this. Compare the total energy radiate on the left side of the peak to the right side. So the peak will be here. Okay, so now we have to compare which side will be have higher or lower energy radiated. Okay, so here will be the middle line. So the left side will be here. Will be here. And then the right side will be here. Okay, so here the total energy radiated for the right side is higher compared to left side. Okay, so why? Give a reason. Okay, so you can see here, we actually compare the area under the graph. Okay, so area under the graph, which is bigger, showing that the total energy radiated will be higher. Okay, so here, because area under the graph at the right side is greater than left. Okay, so this will be the question related to our learning standard 1. Okay, so now we go to our learning standard 2. Okay, so the learning standard 2, you have to able to describe the quantum of energy. Okay, so here will be also the topic related to electromagnetic spectrum. Okay, so just now we explained one of the electromagnetic spectrum already. So actually we have two types of electromagnetic spectrum. So the first one will be the continuous spectrum. And we already discussed this type of spectrum in the learning standard 1. And you also already learned it at very detailed in subtopic of 5.7 in the chapter 5 from 4. Okay, so you can see here, the spectrum we discuss here will be at the region of visible light. Okay, so the visible light spectrum is considered continuous because there will be no any gap between each color in the spectrum. Okay, so the visible light region will be have seven type of color. So where the shortest wavelength will be for the violet light and the longest one will be for the red light. And there will be no any gap between the color in the spectrum. So that we know as a continuous spectrum. Okay, so another light of spectrum will be explained by the new ball, just how we explained already. So the light spectrum is actually able to explain by the new ball, who is one of the scientists development in the quantum theory. Okay, so the line spectrum show in the electromagnetic radiation of specific frequency of light. Okay, so what means by this? So you can observe this example. Okay, so the background of the spectrum is actually dark color. And you can see there are many different lines with different color. Okay, so the different line with specific color and specific position is due to the energy emitted of the electron transition with different frequency. So you can just look at this diagram. So we have shell 2 and shell 1. Okay, so here you can imagine that. So at the stable condition, the electron will be always stay closest to the nucleus. But when it is excited, when the energy is provided, so it will be jump to the higher level, energy level. For example, from 1 to 2. Okay, so the electron at excited state, where will be at higher energy level, which will be represented with N. So it is actually unstable, and it will be go back to the lower energy level. So when the electron return to the lower energy level, it will be emitting the radiation with certain energy, where we're using symbol E. Okay, so the energy will be related with or directly proportional to the frequency of the light emitted. And this will be going to discuss detail in few slides later. Okay, so every line in the light spectrum is caused by a transition, or just now explained already. So the electron will be excited from and jump from lower energy level to higher energy level. Okay, so when the electron go back to lower energy level, so the radiation will be emitted. So it will be appear as one of a line in the line spectrum. And the specific line formed in the line spectrum will be have specific frequency of light. So this is why you can see different line appearing in the light spectrum because of the electron transition between two different energy level. Okay, so now we go for the Planck quantum theory. Okay, so here the electromagnetic radiation emitted by black body is not continuously, but is in discrete, which is also can known as separate packet of energy. Okay, so according to the classical theory, physics theory, okay, so the electromagnetic radiation is actually continuous. So they are actually all combined together. But in the Planck quantum theory, the energy is actually in discrete. In discrete, that means separate with different bundle. Okay, so here we know as the quantum energy. Okay, so you can see each packet is called quantum of energy, just like this figure. Okay, so this means the energy of the electromagnetic radiation is quantized. So quantized, that means they have the fixed energy. Okay, so the light energy exists in the form of the energy packet we know as the photon. So that means the quantum energy can also known as the photon. So photons are light energy transfer in quantum of energy. So the energy size of radiation depends on its frequency, as explanation just now. So the energy radiated will be depends on the frequency, which is actually directly proportional. Okay, so you can see here we have frequency for transition electron with energy level 4 to energy level 1. Okay, so here the energy emitted will be highest as a frequency for the light emitted when the transition of electron from higher energy level where equal to 4 to the lower energy level where n equal to 1. So the E will be directly proportional to the F here. Okay, so the higher the energy of light wave, the higher the energy quantum of photon. So the energy quantum of photon here will be E. The frequency of light will be using symbol F. Okay, so according to this assumption, the quantum of energy with symbol E for radiation or frequency F can write as this formula, E equal to HF. So where the E will be, as mentioned, E will be photon energy, F will be frequency, then the H will be represented as a Planck constant with value of 6.63 times 10 power negative 34 joule second. So the value for H or Planck constant is fixed with this value. Okay, so since the speed of electromagnetic radiation, we're using symbol C. So where equivalent to value of 3.0 times 10 power 8 meter per second. So here we have the formula, speed of light equal to F lambda. This formula you also learned already at the chapter 5, form 4. Okay, so the wavelength can be related to frequency with this arrangement where wavelength equal to C over F. And we substitute the equation to E equal to F HF. So here actually supposed to be F, here will be supposed to be lambda. Okay, so when we substitute the F with C lambda, we get another formula of energy where will be related to wavelength of the light. Okay, so through these two formula, we can conclude that the energy, quantum of energy or photon energy is directly proportional to F. So for the next formula here, the E will be inversely proportional to the wavelength of the light. Okay, so here the quantum of energy E for the radiation is inversely proportional to the wavelength. So will be this formula. Okay, so we have already finished our second learning standard. Okay, so let us discuss the related question. So the question number 3. So a lamp emits light, red light with frequency 4.29 times 10 power 14 hertz. So how much energy quantum of the photon release? Okay, so here frequency we're using symbol F. Then the question asks you about the energy of quantum. So we with symbol E. Okay, so you have to select the correct equation for substitution of this value. So the equation we are going to use will be E equal to HF. Then the H value is actually fixed with 6.63 times 10 power negative 34. Okay, so it will be this. This will be the value H, and the value F is given by the question. Then you will get the answer where here will be 2.84 times 10 power negative 19 joule. So please give 2 decimal places for your answer with correct unit. Okay, so the question is actually very simple, which just apply the formula you learned just now. Okay, so the question number 4 here is also another calculation question where applying the formula we learned in learning standard 2. Okay, so calculate the photon energy again. Photon energy, you can just stack the symbol. Then you can know which formula you are going to select for your calculation. Okay, so to calculate the photon energy of ultraviolet electromagnetic wave with the wavelength 390 nanometer. So wavelength will be this symbol. Okay, so which formula you are going to use? The formula will be this. So where the H value will be fixed with 6.63 times 10 power negative 34. C will be 3.0 times 10 power 8 meter per second. Okay, so please ensure that you change your wavelength unit nanometer to meter because unit for H and C is in SI unit. Okay, so here substitute all the value and change your 390 nanometer to meter, which will be times 10 power negative 9. So you'll get your answer in SI unit. So E will be energy. So the final unit will be joule. So the answer here will be 5.1 times 10 power negative 19 joule. Okay, then here will be another subjective question I select from paper 2, section A. The question is the trial 2022 from State of Negeri Sembilan. So the question will be like this. Okay, so this is the diagram where showing the parts of electromagnetic spectrum. Okay, so just now we learned already at learning center 2, there are two types of electromagnetic spectrum. The first one will be the continuous spectrum, another one will be line spectrum. So here, the question asks you to take the correct answer in the box provided. So what is the type of spectrum? Showing in diagram 1. So here is ratio, because you can see this is a line in the spectrum. So this will be the line spectrum. Okay, so the line spectrum comparison with the continuous. So this is a continuous spectrum. So there will be not showing any gap between different color in the spectrum, while there will be the gap for the quantized spectrum here referring to line spectrum. Okay, so here answer very clear that there will be line spectrum. Okay, then the next question, based on the diagram 1, name the physics quantity represented by arrow. So the arrow will be here. Okay, so what is the quantity physics showing by the arrow will be actually the lambda. Okay, so the lambda is actually represent the wavelength. Okay, so the answer here will be wavelength. Okay, so the question C1. Okay, so underline the correct answer at the statement below. Okay, so here, besides the Max Planck and Albert Einstein, so who is another physicist who introduced the idea of quantum theory? I think this will be very clear. Just how we explained already, we have 4 physics development for classical theory, and another 4 will be development for the quantum theory. Okay, so here answer very clear will be Louis de Broglie, 1 mark. Okay, then the next question will be, what happened to the photon energy if the frequency of light increases? Again, first step, you can give the symbol for the terms related. So the photon energy we using symbol E, and the F will be for frequency. So what is the changes for the E if the frequency increases? So here, so this will be the formula for chapter 7. You are going to see in the answer sheet for the question in paper 2. So you have to select the correct formula. Okay, so then you can compare the relationship between E and F. So here you can see very clear that the F is actually directly proportional to E. Okay, so here answer will be increases. Okay, so here, before we go for learning center 3, we can take a break first. Okay, so we come back after this. Okay, so welcome back everyone. So let us continue our learning standard 3, where you must able to explain the wave particle duality. Okay, so here there will be the equation related to the de Broglie wave. Okay, so just now we already explained that the Max Planck is one of the physics where consider the light as a wave and also behave as a particles. So the Louis de Broglie is also one of the physicists where also agree with this statement given by Max Planck, where the light has natural properties of wave and also the particles. Then matter also has the characteristic of the wave. So that means that the light can have two properties which can behave as the wave and also the particles. Okay, so here we want to try to derive the equation of de Broglie, where is actually able to explain the wave particles duality theory here. Okay, so here from the Planck's quantum theory, so the energy of the photon is given by this formula. So where we already discussed in the learning standard 2. Okay, then the second equation we are going to relate to the formation of this equation will be E equal to mc squared. So where this Einstein's spatial theory of relativity, and this E equal to mc squared is actually the nuclear energy formula you learned already at chapter 6 form 5. It's the previous chapter you learned already. Okay, so here you can relate momentum equation where P equal to R equal to mv. Actually, it's mv first initially. So the momentum we're using formula mv, where you learn already also in the chapter 2 form 4. So the v we using simple c because here the speed we use is actually speed of light, where equivalent to 3.0 times 10 power 8 meter per second. Just now we explained already. Okay, so when you substitute in the equation E equal to mc squared, so you get your nc times c become pc. So we form equation E equal to pc, where we form the equation number 2. Okay, so now we relate equation 1 and 2 so that we can get the equation of de Broglie, where can explain the wave particles duality theory. So look at the formation of this formula when 1 equal to 2. So the PC from equation 2 will be equivalent to hc over lambda, where you can get from equation 1. So you cancel out the c. So you can get the equation wavelength equal to h over p. So where the p is momentum of the particles, and then lambda will be the wavelength. So this is called as the Broglie wave equation. Okay, so here we want to use the equation we derived just now to explain the wave particles duality. Okay, so from this equation, the wavelength associated with a mass of the particles with its velocity. So you can see here v times v, so we get p. So the v here is actually equivalent to c because the speed of the light is equivalent to 3.0 times 10 power 8. So therefore, this formula can be used to deduce the light has a momentum and exhibit as particles property. This also showing that the light is duality in nature, which is able to behave in some situation like wave and others like particles. And this will be known as wave particle duality of light. Okay, so the experiment evidence tabulate below is showing the wave can behave as a particle and the particles can behave as a wave. Okay, so the experiment where showing that the wave behave as the particles will be the photoelectric effect experiment. And this experiment will be discussed detail in subtopic 7.2, where is the experiment discovered by or invented or explained by Einstein. Okay, then another experiment here will be the Young double slit experiment, where able to show the interference of wave and also the diffraction of wave, where showing that the particles can behave as a wave. Okay, then the next here will be formation or development for the electron microscope. Okay, so due to the properties of the electron that can diffracted. Okay, so you can look at this figure. It's the experiment related to diffraction. Okay, so the electron microscope uses electron beam accelerate as a source of light. So because the electron wavelength can reach 1 times 0 times 10 power 5 times shorter than visible light. Visible light photon, so electron microscopic has higher resolution power than light microscopic. Okay, so here will be the comparison between the light microscope you use in laboratory with the electron microscope. So first, the light source for the light microscope will be the visible light, while the electron microscope will be the electron beam. So the resolution for the light microscope will be lower compared to the electron microscope. So therefore, the magnification for the light microscope will be able to make up to 2,000 times. So for the electron microscope will be up to 1 million. So the electron microscope able to magnify the object much larger compared to the light microscope because of the electron beam through the diffraction. Okay, so here will be the question related to learning standard 3. Okay, so here is a calculation question where we're using the de Broglie wave equation. Okay, so if the momentum of an electron given as 3.4 times 10 power negative 28, so determine the wavelength. So again, you can using a symbol to showing for the term so that you can select the correct equation. So here momentum will be small letter p. Then the question asks you to find the wavelength with symbol of lambda. Okay, so the equation will be this, where we already discussed just now. Okay, so here you just substitute h with value 6.63 times 10 power 34, power negative 34, with the wavelength, momentum given in the question, where will be 3.4 times 10 power negative 28. So you will get the value, which is 1.95 times 10 power negative 6 meter. Okay, so here we go for our last learning standard, where will be learning standard 4 and 5. So learning standard 4, you must able to explain the photon concept, where is actually quite related or similar to the quantum theory, Planck quantum theory we learned already at learning standard 2. Then another one will be the problem solving related to the photon energy and photon power. So here you will be using two equations for the problem solving. Okay, so here the photon theory will be like this. Okay, so a photon is a discrete bundle of energy or quantum of the electromagnetic beam. Actually, this one is quite similar to the Planck quantum theory we explained just now. So when the bundle, discrete bundle of energy we know as quantum energy. So the photon is actually quantum energy. So you can look at this figure, which is similar to the learning standard 2 I showed you just now. So this is the discrete bundles of energy. So where is actually represented as a photon. Okay, so the photon energy is directly proportional to the frequency of the electromagnetic wave. So as the quantum energy is same as the photon energy. So here, just now we have a formula where E equal to HF. Therefore, the photon energy will be direct proportional to the frequency of light. So here you can, using this graph to relate the photon energy and frequency. So the photon energy will be also using symbol E, just like the quantum energy we explained just now. Okay, so this will be the formula related to photon energy, which will be E equal to. So we discussed already where we relate the wavelength with the photon energy with formula E equal to hc over wavelength. So the graph to show the relationship between the E photon energy and wavelength will be like this, which is inversely proportional between E and lambda. Okay, so here there is another new formula actually where we haven't discussed from learning standard 1 until 4 just now. So here will be the energy, actually is the power. Here we need to change to is the power of photon with symbol capital P. Just now the momentum we're using small letter p, but for power of photon we're using capital P. So where the equation will be P equal to NHF. So the H we know already, it will be Planck constant with value of 6.63 times 10 power negative 34. Then the frequency here referring to the frequency of light. Okay, so the N here will be referring to numbers of photons emitted per second. So this will be the new formula for you to learn in this last learning standard 4 or 5 here. Okay, so here we go for problem solving related to the formula we already go through in learning standard 1 to 5 here. Okay, so here will be the question. Okay, so the two photons of light P and Q have wavelength of 400 nanometer and 750. So that means P has the shorter wavelength compared to Q. Okay, so here which comparison is correct about the energy? So again, so here energy will be E. Wavelength will be with unit of lambda. So that means we need to using the formula to relate E and lambda, where is actually inversely proportional to each other. So this will be the formula and this will be the graph. So that means that when the wavelength decreases, the energy will be increases. So here, the wavelength for P is actually shorter. So the E is actually higher. So that means P is greater than Q. So the answer here will be actually A. Okay. Then the next question here, question number 8. So it's also the objective question. Okay, so a mercury lamp may produce purple and green light with frequency of 7.41 times 10 power 14 hertz. And for green light, the frequency will be 5.49 times 10 power 14 hertz respectively. Okay, so again here, we need to compare the energy possessed by purple and green light. So that means we need to relate E with F. So again, the formula we relate here will be E equal to HF, where E and F will be directly proportional. So here, the purple color light have higher frequency, so the E will be higher. Okay, so here, the first purple light energy equal, so will be wrong. B, purple light energy is smaller than green is wrong also. So the answer here is very sure that should be purple light energy is greater than green light. So answer here is very clear, will be C. Okay, so here the next question, question number 9. Okay, so here will be the calculation question. So how many photons are emitted per second? Okay, so numbers of photons emitted per second, we using symbol n. So the question actually asks you to find the n. Where will be the last formula you learned already at Learning Center 5? Okay, so and here by a 50 watt green light lamp. So 50 watt here, when you see watt is, it actually represent power, right? So the power here will be symbol capital P. Okay, so what is the formula you are going to use? Here the question given us, the P equal to 50, H equal to 6.63 times 10 power negative 34. This is the fixed value, and then the frequency is given by the question, where will be F equal to 5.49 times 10 power 14 hertz will be this. So now we have to find N. Okay, so we will apply the last formula we learned. So P equal to N HF. We will arrange the formula. Okay, so here we'll get N equal to 50 divide 6.63 times 10 power negative 34 and 5.49 times 10 power 14. So all of this value is already in SI unit. So N actually will be no any unit. It's the numbers of photon. Okay, so here, after press calculator, we'll get 1.37 times 10 power 20. So as mentioned, here will be the numbers of photon. There will be no any unit for the answer. Okay, so we go for our last question for today's subtopic. This will be the comparison question, question number 7 for MRSM 2022. So this is just a partial question where related to subtopic today we discuss. Okay, so here diagram 7 shows a hydrogen line spectrum. Okay, so this is a line spectrum. That means that there will be a gap between there will be a line in the spectrum. Okay, so the color line form has specific wavelength, just how we mentioned already, frequency and quantum energy. Okay, so here asks you about the definition of quantum energy. So what is a quantum energy? So it's a discrete energy packet and not continuous energy. Okay, so this will be the answer for your reference. Okay, then as mentioned already, so here again is a comparison between the line spectrum with the continuous spectrum. So the continuous spectrum will be no any gap between the color or light, while the line spectrum will be have a gap, and you'll be showing the line with specific wavelength or frequency. Okay, so here will be the calculation question. So a color line from line spectrum of hydrogen atom has a wavelength about 4.86 nanometer. So here the question given us the value of F. So determine the photon energy. That means the question asks you about the E. Okay, so the H and C is given already. Okay, so here the 486 nanometer referring to the blue color light. Blue color line in the line spectrum. Okay, so you have to select the correct formula. So here's supposed to be, so the 486 nanometer will be actually wavelength. So we using formula number 5 here. So we just substitute value H, value C, and value of lambda. Okay, so here will be the substitution. Okay, then press your calculator. You will get the answer. 4.09 times 10 power negative 19. Okay, so 2 marks. The first one will be given for substitution. Second marks will be given for answer in minimum 2 decimal places with correct unit. Okay, so please using capital J represent for unit joule. Okay, so we go to the last question for today's subtopic. Okay, so based on your answer in 7B, if the numbers of photon emitted is 3.37 times 10 power 18 per second, so calculate the output power. Okay, so here, this will be referring to symbol N, and here it will be P. So the question asks you about the value P. Okay, so which formula you are going to select? So it will be equation 6. Equation 6. Okay, so here, the E equal to HF, you already get through question B1. From B1, you already get the answer. Okay, so here we're using P equal to NE. So N given by the question, and then the E get from 3B1. Okay, so again, just press your calculator. So you get answer 1.38 watt, or you can using symbol joule per second to represent watt. Okay, so again, answer must be minimum 2 decimal places with correct unit. Okay, so that's all for my sharing today. So before I end for the live today, so I would like to share to you the e-schedule link for today's lesson. Okay, so so I say again, the link is schedule. Okay, so the link is already able to get through the chat room. Okay, so make sure that you fill up the link within 30 minutes just after the lesson end with any email you are available. Okay, so that's all for my sharing today for subtopic of 7.1. So please click like and share the link for today's lesson for your friend, so that more of your friends able to get the benefit for my sharing today. Okay, so again, don't forget to follow the next physics classes, where the class Form 4 Physics in Bahasa Melayu will be held in every Friday, 9:30 p.m. Then another lesson will be Form 5 Physics in DLP, just like today, will be on next Sunday, 8:45 p.m. So we continue by Cikgu Hasnitah. Okay, so here I saw the reply from Daniel. So thank you, Daniel, for follow my lesson. Okay, so here will be all the information or the question related to subtopic 7.1. Okay, so again, I would like to thanks all the students who is continue together with me until now. Okay, so see you again. Bye-bye.